In this video, we will be doing long answer 2 from midterm 2. The question is, 100 milliliter buffer solution is 0.1 molar NH3 and 0.1 molar NH4 plus. Assume no change in volume. The Kb of NH3 is 1.8 times 10 to the negative 5. So what we are asked to do is find the pH of the original solution. What you're going to have to know for this problem is the Henderson-Hasselbalch equation, which is pH plus pKa plus log base over acid. What you have to know is that pKa is the negative log of Ka. You're also going to have to know that pKa plus pKb equals 14, and that NH3 is your base and NH4 is your acid. Since you're given the Kb of NH3, you're going to want to plug that into this equation. So you have pKa plus pKb is equal to 14. So therefore you have pKa plus and pKb, that is negative log of Kb. So you put negative log, you remember your Kb is 1.8 times 10 to the negative 5, and that is going to equal to 14. This comes down to pKa plus 4.744 is equal to 14. And from there, it's just math. So you have pKa is equal to 14 minus 4.744, which ends up being pKa is equal to 9.256. Since you're already given the concentrations of NH3 and NH4 plus, you could just then plug that into the Henderson-Hasselbalch equation, which is pH equals pKa, which you just found out, which is right there, plus the log of the concentration of your base, which is NH3, and you know that is 0.1 molar. So 0.1 molar over the concentration of your acid, which you also know that it is 0.1 molar. That you just plug it into your calculator, and that is 9.256 plus the log of 0.1 divided by 0.1, and it is just your pKa. So for the first question, your pH is equal to pKa, which is 9.256. And that is the pH of your original solution. In the next part of the question, you are asked if 0.004 moles of KOH is added to the solution, then what is the pH? The first step in figuring out this problem is finding the amount of moles of NH3 and NH4. So you know that molarity is equal to moles over liters of solution. And from the problem, you know that there are 100 milliliters of solution and 0.1 molar NH3 and 0.1 molar NH4 plus. So what you want to do next is plug this information into the equation up here, and you know that you have 0.1 molar NH3. That's going to equal to the amount of moles of NH3 over, and you know that you have 100 milliliters of solution. In order to convert that into liters, you have 100 milliliters, and for every 1,000 milliliters, you're going to have 1 liter. So that turns out to be 0.1 liter. So you have 0.1 liter of solution. You could just multiply this over here to find out your moles. So then you have 0.1 molar NH3 times 0.1 liters is going to give you your moles, and your moles turn out to be 0.1 moles of NH3. And the same goes for NH4 plus, since the concentration are the same. So then you know that you have 0.01 moles of NH4 plus. After doing that, you're going to want to use the Henderson-Hasselbalch equation once again. So remember, it's pH is equal to pKa plus log the concentration of your base over the concentration of your acid. Since you already solved for pKa in the first part of the question, you know that that is equal to 9.256. And since you are adding a strong base, it's going to fully dissociate, causing the concentration of your base to increase and the concentration of your acid to decrease. So it's going to be plus log, and your initial concentration of your base was 0.01 moles, 0.01 moles of NH3, but you're adding 0.004 moles of KaOH. Therefore, you're going to add them because it is a basic solution, so plus 0.004 moles. And you're going to subtract it from your concentration of your acid. That's going to be pH. So therefore, pH is going to equal to 9.256 plus the log of 0.014, and that's your base, over your number of moles of your acid, which is 0.006, and that gives you a pH of 9.62. Comparing this to your initial pH of 9.256, since you added a basic solution, it only makes sense that your pH would increase, making your solution more basic. For the third part of this question, we will be calculating the pH if you add 0.003 moles of HBr to the original solution. So remember that you already calculated your moles of NH3 and your moles of NH4 plus, which both turn out to be 0.01. In this case, since you're adding HBr, which is a strong acid, you know that's going to fully dissociate, and you're going to get H plus, which increases the concentration of your acid and decreases the concentration of your base. So when using the Henderson-Hasselbalch equation, you are going to subtract the amount of moles of HBr from your base and add them to your acid. So since you already figured the pKa, which is 9.256, you're just going to add plus the log of your base, which was the moles of NH3. So you have 0.01 moles of NH3 minus the amount of moles of HBr, which is 0.003. And for your acid, you're going to have 0.01 moles of NH4 plus 0.003 moles of HBr. And that is going to give you your pH. So this, you just plug it into your calculator and you get 9.256 plus log of 0.007 moles of your base and 0.013 moles of your acid, and that gives you a pH of 8.99 after you add 0.003 moles of HBr to your original solution. Once again, since you added an acid, it only makes sense that your pH decreased as a result of that. So when calculating buffer solutions, you can never go wrong using the Henderson-Hasselbalch equation. So just remember, the equation is pH is equal to pKa plus log of your concentration of your base over the concentration of your acid.